and I believe this will be the last chapter that will be included on exam 2, if I'm not mistaken. So this will be the last one. So I think it's 6, 7, and 8 for exam 2 coming up couple weeks, I think, if I'm not mistaken, in that ballpark. All right, so gases here. Obviously, we're going to talk about the state of matter where things are flying around. And as they're flying around, they're causing collisions. These collisions have a direct relationship on pressure. So as we have more collisions, they go up. We typically see the pressure go up as a result of that, and vice versa. Obviously, if the collisions go down, then we see a drop in the pressure. So let's talk a little bit about substances that exist as gases under normal conditions. When we talk about normal conditions, this is kind of everyday room temperature type conditions, and that is a pressure of 1 atmosphere, which is an ATM, and a temperature about 25 degrees Celsius. So under normal sort of room temperature conditions, ionic compounds typically will not exist as gases. And that is because they are held together by probably one of the strongest attractive forces, which is the opposites attract, the positive and negative attraction from those charges. So what typically would happen with an ionic compound is you could heat the heck out of it, and pretty much it will just start to melt first before it will even try to get into the gas phase. And it just really will never probably get into the gas phase at all. It will just, like I said, just start to melt before it will jump into the gas phase. Now, the behavior of molecular compounds, which are guys that share electrons, are a little bit different. There are certain compounds that are just gases straight up, like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, which is NH3, and methane. Those are all gases. The difference is, though, a good majority, though, of molecular compounds, which again are these guys that have covalent bonds, they typically are liquids, are solids at room temperature. But one of the major sort of differences between a molecular compound and an ionic compound is it is much, much easier to turn a molecular compound into a gas than an ionic compound. And the nice, easy example is this thing right here. Not this pipe, but it is water. Yes. So we could boil water pretty easily, and water will turn into steam, which is the gas phase of water. So we could very easily turn something like water, which actually shares electrons. So when we have something like water, water is a polar compound where oxygen is more negative, hydrogen is more positive. And when water molecules get together, they're actually held together by opposite attraction between water molecules. The negative side of one is attracted to the positive side of another. That is what is known in the case of water as being hydrogen bonded, or hydrogen bonding happening. And that is what is referred to as an intermolecular force. And an intermolecular force is a force that holds one molecule together with another. And it could be the two of the same molecules, it could be two different molecules, but it is the force that holds basically how one molecule will interact with another. And that is different than what we have if we just looked at one water molecule. The covalent bond between the oxygen and hydrogen, where they're sharing electrons, that's what's known as an intramolecular force. And an intramolecular force basically is the bonds that hold one molecule together so don't fall apart. And in the case of water, that is the sharing of electrons between the oxygen and hydrogen on each side there that holds that one particular molecule together. Now, intermolecular forces are always much weaker than intramolecular forces. And we know that because, again, when we heat water, the first bond that breaks is the bond between these two water molecules. And that allows this water molecule to go off into the gas phase, allows this water molecule basically to go off into the gas phase. If it was opposite and you heated water and the intramolecular bond was weaker, every single water molecule would break apart between the hydrogen and the oxygen, and you would create hydrogen gas and oxygen gas, which does not happen. And a simple example is that if you boiled water before, you could get to like the pasta making part of it. Otherwise, if you produce hydrogen gas and oxygen gas while you're boiling water, you would never get to the making food part of it because it would probably explode. So we don't separate or break water by just simply boiling it or stuff like that, but we can break that intermolecular force much, much easier. And that's also why ionic compounds pretty much do not go into the gas phase, because that electrostatic attraction, that positive negative attraction, is this one of the strongest intramolecular forces you could have, and it's just not gonna, you're not gonna be able to basically break it apart into the gas phase. So the general rule is the stronger the attraction between molecules, the less likely it will exist as a gas under ordinary conditions. That's why something like methane is a gas that comes out of that right there under normal conditions, because it's held together, one methane molecule and another one, by like a super weak force. Like you sneeze at it or just look at it wrong, and it's enough to just make it kind of go away, and they won't hold together very strongly. And that's why they are gases. That's why a lot of organic molecules, which are nonpolar, are gases. Things like propane that you might be used to, butane, methane. These are all gases, and that's because they're held together by very, very weak forces. So when you have two of those molecules together, it doesn't take a lot for them basically to separate off and go into the gas phase and make a gas. Now, substances that are found as gases under normal conditions, we have our hydrogen, nitrogen, and fluorine and chlorine. Those are our diatomic molecules, which are our elements. They are also gases, how they naturally exist. Ozone, which is O3, is also a gas. And obviously on our periodic table, group 8, which is our noble gases, those are also gases. Noble gases are monoatomic gases, which means they come as ones. And again, hydrogen, nitrogen, oxygen, fluorine, and chlorine comes as twos, which are diatomic. So here's the kind of shaded guys are the ones that are in normal conditions, would be found as a gas. This is a good time to talk about the difference between two words, which is a gas and a vapor. A gas is a substance that under normal conditions would actually be a gas, or be a gas under those conditions. A vapor, on the other hand, is something that normally exists under normal conditions as like a liquid or a solid, for example. So again, back to water is an example of that. Water normally exists as a liquid under normal conditions. So when we turn it into a gas, we call it water vapor a lot of times because of that, not water gas, because it sounds funny. But we call it water vapor or steam. And okay, so we're going to continue on here, and let's get into gases a little bit. One of the important sort of properties of a gas is pressure, and pressure is the main property of gases. And one instrument that's used to measure pressure is a barometer, and a barometer, traditional barometer, is used to be a pool of mercury, and it used to have like a glass tube in there. And basically, as the atmospheric pressure would apply down to the mercury in the tube would rise. Nowadays, a lot of schools are taking them out because it has mercury in it, but maybe there's still a barometer hanging around somewhere. Some of the important units of pressure is an atmosphere, 1 atm. 1 torr or a millimeter mercury are two other common units of it. A torr is named after the guy who invented the barometer. And a millimeter mercury is because, again, on a barometer, there's also used to be like a ruler, and you would measure where the mercury was in the tube with a ruler in millimeters of mercury. Centimeters of mercury are inches of mercury. So millimeters of mercury is a very common sort of unit. A torr and a millimeter of mercury are basically a one-to-one conversion. So if you need to convert between those units, you basically just change the units. The number stays the same. The relationship between atmospheres, millimeters of mercury, and a torr 1 atmosphere is 760 millimeters of mercury, and that equals 760 torr. That means that if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by the 760 number. That will cancel out the atmospheres, and that will give you millimeters of mercury or torr. And if you have millimeters of mercury or torr, and you want atmospheres, you're going to divide by the 760. And that will get you atmospheres in terms of the unit. That 760 number is kind of an important number. It allows you to do the conversion between the different units. And again, either multiply or divide, depending on which way you are going there. Any questions? There's obviously other units of pressure that we don't deal too much with in this class, like PSI is pounds per square inch. There's also bar, which is pretty close to an atmosphere, like 1.01 to 1. So those are some other units, kilopascals, pascals. But for here, those are the big 3 units: atmospheres, millimeters of mercury, and torr. There's a much prettier picture of the barometer. Again, atmospheric pressure coming down on the mercury, mercury rising, hence the name. You sometimes heard that. By the way, mercury has an unusual meniscus. It actually goes the other way. It goes upwards, downwards. Meniscus, and you would reach from the top of the meniscus there. So we're going to talk about gas laws now. And when we talk about gas laws, there really is and the first gas law we're going to look at is Boyle's law. And Boyle dealt with pressure and volume, and he kept temperature constant in this case. And what Boyle saw was a relationship of this. If you have gases in a really small volume or a small volume, that means that all your gas molecules are pretty close to each other. That means there's probably going to be a lot of collisions. People are going to start banging into each other and banging into the container. And because of that small volume, we would see an increase in the collisions, and that should also show us an increase in the pressure. So as the pressure goes up, the volume goes down, basically. It's the opposite sort of relationship here. Opposite to that is as the volume goes up, you have a little bit bigger of a volume. Your gas molecules are now going to be spread out a little bit more. It's going to take longer for collisions to occur. And what we typically will see is the pressure actually will go down when the volume goes up. So the relationship that Boyle saw was basically as one goes up, the other goes down, basically, in that case. And we could basically relate Boyle's law with this equation that we see on the bottom. Another interesting aspect of Boyle's law is if you keep the temperature constant and you do any type of pressure or volume measurements and you multiply them together, you always get the same number. So if you did a bunch of pressure volume measurements under same temperature and you multiply the pressure and volume numbers after each measurement together, you'll always get the same number. So it's sometimes referred to as a proportionality constant. But what that allows you to do is actually come up with an equation like this, which is Boyle's law. It is P1 V1 equals P2 V2. This is kind of like before conditions, after conditions. The pressure here does not matter in terms of units. It could be any unit you like. The only thing that matters is it needs to be the same unit on both sides. Otherwise, they will not cancel. So if you have like an atmosphere and a millimeters of mercury, you got to get them both into whichever one you choose. Both into atmospheres, both into millimeters of mercury before you go into the equation. Same thing with the volume. It could be any volume you like. It could be milliliters. It could be liters. But again, it does need to be the same volume on both sides in terms of the units. So everything cancels. So again, there's kind of no restrictions on the units here. One goes up, one goes down in terms of the relationship. And that's what we see here at a small volume, a much higher pressure. And at a much larger volume, our pressure, which is over here, is much, much smaller. So that is your Boyle's law of relationship. All right, so why don't you give it a go here? An inflated balloon has a volume of 0.55 liters at sea level, which is 1 atmosphere. It rises to 6.5 kilometers, where it has a pressure of 0.4 atmospheres. Assuming that the temperature remains constant, what is the final volume of the balloon? Take a moment, see what you come up with here. At this point, pretty simple to choose the right one. Kind of a good idea to pull out the information and label what it is, because very often it will kind of show you almost like the gas law that you should use. Here we do have a volume that is 0.55 liters. It goes with 1 atmosphere, which is a pressure. It rises to 6.5 kilometers, which is not useful at all, really, in this problem. We have another pressure of 0.4 atmospheres, and we are looking for a final volume here. So again, if you kind of look at it there, you can kind of see Boyle's law in front of you, and it kind of will point you. Doesn't matter which ones you make 1 and 2. So typically speaking, just in the way it's ordered in the problem is kind of what we call 1s and 2s. So call those guys 1s, this side 2s. Now, one of the things in terms of these gas laws and rearranging the equations, remember that when you cross over, uh, everybody ends in the opposite location of where they started. So what I mean by that is here we are looking for V2. And although this is not really written as a fraction, those guys are considered to be on top of the fraction. So I need to move P2 to the other side. It ends up in the opposite location. Instead of being on top, it'll end up on the bottom. And that will give me P1 V1 divided by P2 equals V2. We're essentially dividing both sides by P2. It ends up in the opposite location, basically, in that case. So that's a quick way to arrange some of these gas law problems. If you need to move something to the other side of the equal sign, it will just end up in the opposite location of where it was at. If it was on top, it'll end up on the bottom. If it was on the bottom, it'll end up on top. So it's a quick way you can kind of rearrange the equation. So now I want to plug in our numbers here. We do want to check units here, atmospheres and atmospheres. So both of our pressures are good. So we'll go with 1 atmosphere on top times our 0.55 liters divided by our 0.040 atmospheres. Atmospheres on top and bottom will cancel. That's going to leave us a volume that's in liters based off of that unit. And that's basically 0.55 divided by 0.4 gives us a 1.4 liters in this particular case. First off, any questions on that there? Now we could also, since we understand the relationship of Boyle's law, see if it makes sense our answer. Here the pressure went from 1 atmosphere to 0.4. So my pressure went down, which means my volume should go up. Started at 0.55 liters, ended at 1.4. So that's good, right? So sometimes a good idea to check just that doesn't make sense. So make sure you didn't invert some numbers, which is very common errors when you're using gas laws. Any questions on that there? Yeah. You do get 1.375 on your calculator. Here's significant figure wise. Everything here is basically 2 sig figs. Yeah. So based on just the normal rules, we would end up at 2. Yeah. What I was saying is it doesn't matter which ones you call like the 1s and the 2s, as long as you keep obviously the information that goes together. So for example, I called 0.55 liters and 1 atmosphere like P1 and V1. I could have called that P2 and V2. It wouldn't matter for that reason. But you do have to keep obviously whatever information that goes together. But it doesn't really matter if you call like them 1s or 2s, as long as whatever information goes together stays together. Honest, honestly, the best rule of thumb for these type of problems is just to kind of label them in the order it is in the problem. So whatever kind of values come to first is typically what people will call like the ones, and whatever comes second is typically what people will call this too. So just going in the order of the problem is probably the easiest way not to have to worry about it. Something like that. Other questions? Okay. All right, the next law we're going to talk about is our friend Charles' law. And Charles' law dealt with volume and temperature and held pressure constant. And that is Charles' law there on the bottom there. V1 over T1 equals V2 over T2. So what happens in this situation is when we have volume and temperature, if I were to raise the temperature of my gas molecules, right? Let's say in this container, gas molecules fly around faster or slower if I raise the temperature? They would go faster, right? Like lighting a match under you, that old saying, right? You'll move faster, right? So these gas molecules would start to fly around faster. And if that volume, for example, doesn't move, that should then start to increase the number of collisions that you would have. But that is not good because that would also cause a rise in pressure if the volume didn't move and you had a lot more collisions. So because this is at constant pressure, what happens when you raise the temperature is it will actually cause the volume to go up. And by causing the volume to go up, what happens is it gives those gas molecules a lot more room to fly around in. Even though they're moving faster, they now have a greater area to fly around in. And that's going to keep the number of collisions pretty much the same as it was previously. And that's how it's able to keep the pressure constant, is by the volume adjusting when we raise the temperature. So what we see is as the temperature goes up, we will see the volume sort of go up as well. Opposite would be true if we had some gas molecules here and we lowered the temperature. When we lower the temperature, the gas molecules are going to fly around a lot slower, which means it's going to have a lot less collisions. So that's going to cause the pressure actually to change. And we do not want the pressure to change. So what happens in that situation is, once again, the volume actually adjusts to a smaller volume, which means that although they are flying around slower, there's still going to be the same number of collisions, and that's going to keep the pressure constant. So in Charles' law relationship, what happens is it's the volume that adjusts to allow the pressure to remain constant and have the same number of collisions when basically you adjust the temperature. Now, there is actually a gas law, which is known as Gay-Lussac's law, which is very similar to this one, which is P1 over T1 equals P2 over T2. This is at constant volume. And in this situation, when we increase the temperature, our volume doesn't change because it's constant. So we've got like a rigid container and volume's not going to be able to change. It's just fixed. And because of that, the gas molecules will start to fly around faster, cause more collisions. More collisions will lead to an increase in pressure. So in this relationship, when the volume is fixed and you increase the temperature, you will actually start to see the pressure start to go up because there's no getting around it. There's just going to be a lot more collisions happening, and that's going to cause a lot more pressure. Same thing will happen in this situation, if you lowered the temperature. If you lower the temperature, our gas molecule is going to move a lot slower. Dramatic drawing, a lot slower moving gas molecule. And that's going to cause a lot less collisions to occur. And when we have less collisions, we will actually see the pressure go down. So these are two laws which are kind of related to each other. Law of volume. And if you change the temperature, you will affect the pressure. And in Charles' law, the volume is not thick. Actually adjusts to keep the pressure constant. Any questions on that there? So one of the interesting relationships that we see in Charles' law is if you make a plot of the volume versus the temperature, it will give you these straight lines. And if you take any of these gases straight lines and you extend their lines all the way back to the temperature, they all cross at the exact same point. They all cross at minus 273.15 degrees Celsius. Converted into Kelvin, we would add 273.15, and that is what is known as 0 Kelvin, or absolute zero, it used to be called, later named after Kelvin. So the result of that is, you could think that, I guess, that when you have any gas law ever, pretty much, the temperature always needs to be in Kelvin. So anytime you have a gas law that has a temperature aspect, like we do in both of these cases here, Charles' law and Gay-Lussac's law, they all have to be in Kelvin. So here, this is constant pressure. So the temperature needs to be in Kelvin. This temperature here needs to be in Kelvin. And it needs to be in Kelvin, and that really should be, when you're doing gas law, it's a no-brainer. Just that should be like the first thing you do. If you have temperature, just put it into Kelvin. Sometimes people do not do that because they come across a problem where they give you the temperature in Celsius and they ask for the answer in Celsius. So logically, people think, well, I could just leave it in Celsius because I want my answer in Celsius, and they gave it to me in Celsius. You cannot do that. You need to convert it from Celsius to Kelvin. You have to then put it into the gas law, and then after you get your answer, convert it from Kelvin back to Celsius. So whenever the temperature goes into the gas law, it has to be in that unit of Kelvin. Any questions on that there? No. All right, so let's try one here. An experiment. There's 452 milliliters of a gas used in a light bulb. It goes from 22 degrees Celsius to 187. What will be the final volume? So see what. Okay, so let's take a look. Now that we have a few sort of gas laws to choose from, we have our Boyles law, we have our Charles law, and we have our Gay-Lussac's law. Once again, pulling out the information from the problem will help point you in the right direction if you're not sure. And again, we're just going to kind of pull out the information as it's written. So in an experiment, we have obviously a volume that is 452 milliliters. It is heated from a temperature of 22 degrees Celsius to another temperature of 187 degrees Celsius, and we're looking for a volume. So obviously, there's no temperature here, so that's eliminated, and there's no pressures here, so this one's eliminated. So it would be Charles' law that we want to use in this particular case. Here, like I said before, we do need to convert our temperature into Kelvin. So again, it's almost, if you got temperature, it should just be the first thing that you do when you're dealing with gas laws. So we're going to add a 273 to our 22, even though it looks like 220. And we've got a 295 Kelvin. Here, we'll also have the 273, and we got a 460 Kelvin there. And our volume is okay in terms of its units. And once again here, I'm just going to call my first set of information the ones, my second set the twos, and we're going to rearrange this equation here correctly, hopefully. And we are looking for V2. So that means that we need to move our T2 to the other side. So again, in this case, our T2 is on the bottom, which means when it goes to the other side, it will go to the opposite location, which is on top. And that means that we will end up with V1 T2 over T1 equals RV2. We're essentially multiplying the T2 to the other side, basically. Yeah, that's what we're doing there. Any questions on that there? Now that we did that, we want to also make sure that when we put our numbers in, we get our correct numbers in the right spot. So we are looking for V1 first, which is 452 milliliters. We actually want T2 on top. So that is our 460 divided by our T1, which is our 295 Kelvin. Here, the kelvins will cancel. That's going to leave us our volume in milliliters. So that's going to be a 452, maybe if my thing turns on, 452 times a 460 divided by a 295. I'll give us something like 705 milliliters as our volume. Again, in terms of Charles' law relationship, in this case, when we look at the temperature went up. That means in terms of the volume, we should also expect it to go up. It started at 452, it ends at 700 or so. So the volume did go in the correct relationship that we see with Charles' law. Question on that there? Yeah. For the final answer is actually in milliliters. The kelvins cancel out since there's two temperatures. Yeah, so these two temperatures here basically cancel out. And those two, what's that? Truthfully, probably we should round up on that, I guess. Since we did convert it to Kelvin at this point, these guys did technically end up at kind of three significant figures, although the 460, it depends on how you write that one. It could be 2 or 3. So 2 or 3 would be okay in this case. I didn't write the decimal there. So technically speaking, this would be 2 significant figures, which means this really should go up to like 710, right? Milliliters, if we round it down. Question, yeah. You do. So it's a pretty much for sure thing. If you have a gas law, you have temperature converted to Kelvin. Even if your head tells you not to, because again, the problem says gives it to you in Celsius and wants the answer in Celsius, and it happens to a lot of people, they go, I don't need to do it. You need to do it. So you got to put it in the Kelvin, you have to put it into the equation and then convert it afterwards. So when you have that conversation later on in the semester, listen to the right answer to do. Any question on that? Well, we can't forget our friend Avogadro, right? He had a number. Why not a gas law? So Avogadro had a gas law. Avogadro's law, when we think about Avogadro's number, that is 6.022 times 10 to 23 atoms equals 1 what? Moles. Yeah, so it would make sense that his gas law involves moles. So Avogadro's law is V1 over N1 equals V2 over N2. And this is actually at constant pressure and temperature. N here is actually the moles. So in gas laws, N equals moles. And volume here is the volume. And the relationship that we see with Avogadro's law is basically as the volume increases, so does the moles of the gas. So they kind of increase proportionally and decrease proportionally as well. So that gas law, like all the other ones there, you could kind of use, plug and chug into it and solve for either volume or moles. And the reason I mentioned that one is when we take Avogadro's law along with Gay-Lussac's law, Charles' law, and Boyles' law, and put them all together, we do get the granddaddy of all gas laws, which is the ideal gas law there, which is our PV equals nRT. Now, PV equals nRT is the ideal gas law. It describes what's going on with an ideal gas. It's an ideal gas. It's pretty much every gas you deal with is an ideal gas because it makes the calculation easier. So we go, hey, that's an ideal gas right there. So under normal conditions, gases will behave ideally. And what that means is under normal conditions, there are 2 main things that make something sort of an ideal gas. One thing is, under normal conditions, the actual volume of the gas molecule itself is relatively small compared to the container is flying around it. And that's why if you look at a lot of gas law problems that you come across, they very often will talk about the volume of the container the gas is in, rather than the volume of the gas molecule itself. And we think of an ideal situation that the volume of the gas is not that important versus the volume is flying around it. The second also important aspect that makes something an ideal gas is in an ideal gas situation, you could have multiple gases in the same container, and we assume that there is like no interaction between those gases. So they're in there like ideally by themselves. You could almost think of them as being in that container by themselves. Even though they're flying around with other gas molecules, we assume that there is no attractive forces between the gas molecules. There's no repulsive forces between the gas molecules. And that's sort of the ideal behavior. So that's two things that make something an ideal gas. And that's ideally how a gas behaves under normal conditions of like normal room temperature and pressures that we deal with. Now, this gas law is PV equals nRT. This is also different than all the gas laws that we saw up to this point. Is not like a twofer. There's not two pressures, there's not two volumes, there's not two temperatures. There's a one and done situation here. One of everything is all we have going on here. It is also the most restrictive gas law in terms of units. So when you use the ideal gas law, the pressure has to be in units of atmospheres. It cannot be in any other unit. The volume has to be in pressure or units of liters. N, which is moles, should be in the units of moles. And just like every other gas law, our temperature has to be in Kelvin. The reason for all that is R. R is a gas constant. And it is a number that you always have available to you when you're doing gas law problems, although they will never tell you that in a gas law problem. They'll never mention the gas constant or anything like that. That is one of those numbers that they just assume you know what it is and that you know you have it available to you. So when you read a problem, you'll never ever probably see the gas constant is this. They'll never ever tell you it. So that number, by the way, is 0.08206, and it has units of liters times atmospheres divided by Kelvin times mole. Nowadays, people like to round this number to 0.0821. I'm good with whichever number you want to use. I personally use the top number because that's the one they beat in my head and I can't get it out. So that's the number I use. But nowadays, books do round it a lot to 0.0821. So you can use either one you want. The nice thing about the gas constant, it'll probably be given to you, which means the units will be given to you, which means if you forget what any of these units are, they're sitting right there. So you could just know that they has to be in those units for everything to properly cancel out. So if you look at the gas constant units, that is the units that everybody else needs to be in there. Any questions on that there? Some other important information about the ideal gas law and relationships is this. We'll start with STP first. STP stands for standard temperature and pressure. And in a problem, if they say, what is whatever the volume at STP, they are actually giving you values for temperature and pressure when they say STP. The pressure is 1 atmosphere. The temperature is 273 Kelvin. So when they say in the problem at STP, those are the actual values that you could use for pressure and temperature and put them into something like the ideal gas law if you wanted to use it there, or any other gas law, by the way, if you happen to use it. Now, there is a really kind of nice relationship that if you are at STP conditions, and you happen to be at STP conditions, 1 mole of any gas will have a volume of 22.414 liters. That is a conversion factor that if you happen to be at STP, you could use, and you might not have to use the ideal gas law. So you could kind of bypass the ideal gas law and use that as a conversion factor. But it definitely has to be at STP. So if the temperature is not 273, the pressure is not 1 atmosphere, you should never use that conversion. If you don't want to worry about using that conversion incorrectly, which might be a good idea, you could always use the ideal gas law in every situation, even at STP conditions, non-STP conditions. You could just throw everything into the ideal gas law and you'll be fine. So you don't have to worry about that conversion if you don't want to. You can throw the pressure and temperature into the ideal gas law and it'll come out the same. So that's why we use the ideal gas law. It really is like a universal gas law. It works pretty much for everybody under all conditions. You could use that gas law. By the way, if we solve for R in the ideal gas law and we put in all of our values at STP, that is how we get the gas constant. That 0.08206 number comes from basically solving for R with all of our STP conditions. Any questions on that there? All right, let's try one here. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a steel container that has a volume of 5.4 liters and 69.5 degrees Celsius. These are formulas that we learned. We got this one here, Boyles. We got Charles. We got Gay-Lussac. Got our friend Avogadro. And then we have our ideal gas law. So we take kind of the same approach here. We're looking for the pressure exerted by that many moles, 1.82. And we have a volume of 5.43 liters and a temperature of 69.5 degrees Celsius. Again, we pretty much have one of everything, which eliminates all these equations and points us in the direction of PV equals nRT. You can kind of see it. Remember, just like this problem, they never mention the gas constant, but that is a value you always have, or a number you always have available to you. So we are going to use the ideal gas law here. Our units of volume is good. It's in liters. Our temperature is not good. So like normal, we're just going to add our 273 and convert it to Kelvin. And looks like a 342.5 Kelvin. And everything else is good. Moles are in moles. By the way, also very common in gas law problems is you're not given moles, but you're given grams. So kind of like we did before, that grams to mole conversion is used a lot in gas law problems, using the molar mass to do that. Also, a lot of times you're given volume in milliliters, and going milliliters to liters is also a very common conversion that you sometimes need to use. Again, 1,000 milliliters is equal to 1 liter. So those are two common conversions that you sometimes have to use here. PV equals nRT. We're going to solve for P, which again, everything's on top, which means when the volume goes to the other side, it's going to go onto the bottom. We're going to divide it to the other side. And pressure would equal nRT divided by V. And putting in our numbers here, we have our 1.82 moles. We have our gas constant, liters, atmosphere, Kelvin, mole. We have our temperature that's been converted to Kelvin, all divided by our volume, which was in liters to begin with, which is good. That means that the moles and the moles will cancel, the Kelvin and the Kelvin will cancel, the liters and the liters will cancel. That will leave me just atmospheres left over. And that's good because that's a unit of pressure. And we go 1.82, I guess I hit the right number, 1.82 times 0.08206 times 342.5 divided by 5.43. Going to yield me a 9.42 atmospheres as our pressure in this case. Questions on that one there? So again, common variations on ideal gas laws, those other conversions you have to do, grams to moles using the molar mass, just like we did in the previous chapter, and also that milliliter to liter conversion, also a very common one. Any questions on that there? Yeah.
This one specifically, you have to use the PV nRT formula.
We do, because
Any questions for the other formulas specifically?
yeah, so like we did some examples earlier, we used those guys. Yeah. Other questions? All right. Now you can look at changes in all three variables, pressure, volume, and temperature. And if we set the ideal gas law equal to each other in two different sort of situations, we get another gas law, which is a really important gas law, which is sometimes referred to as the combined gas law. And that is P1 V1 over T1 equals P2 V2 over T2. Here again, the temperature does need to be in Kelvin. The pressure on both sides just needs to be the same unit. It can be any unit you want. Volume needs to be the same unit on either side. It could be any unit as long as they're the same. We also will usually have the same number of moles on each side, and that's how the moles sort of go away. Why this equation is the one that you should invest your time in remembering is because of this. If you take this equation, and if you want, that is P1 V1 over, if you want to leave the moles in there, you can, N1 T1 equals P2 V2 N2 T2. If you remember this equation and only invest your time into this equation, along with the ideal gas law, you can pretty much get every other equation from it. So for example, if I come across a problem and the only thing I see is pressure and volume in the problem, no temperature, no moles mentioned, or they say they're constant, I just scratch it out and there's Boyle's law. Yeah. If I take this equation and I come across a problem where I see nothing about pressure or moles, I scratch them out on both sides. There's Charles' law. If I take this equation and I come across a problem where I do not see anything about volume or moles, or they say they are constant, I scratch out the volume and the moles on each side. And there's Gay-Lussac's law. And as you could probably get the hint at this point, if I come across a problem and it mentions nothing about pressure or temperature, or they're constant, I just scratch them out. And now I have Avogadro's law. That's all the other laws we just talked about, right? So all you have to do is remember that law, scratch out whatever's not mentioned, whatever is constant, and you'll have the right gas law that you need to use. So if you remember this gas law, which is the combined gas law, with the moles or without the moles, however you want to do it, and you remember PV equals nRT, you'll have every gas law you need at the palm of your hand just from those two equations. You'll be able to solve everything that you need by just remembering those two equations. Any questions on that? All right, it was worth waiting the extra 2 minutes for that, I think. There it is. All right, let's give this one a go here. Consider oxygen gas. We got it at 27 degrees. It has a volume of 9.55 liters, got a pressure of 2.97 atmospheres. We changed pressure to 8.25 atmospheres, and we heat it up to 125 degrees Celsius. What will be the new volume of this gas? So give it a go, see what you come up with. Okay, so let's take a look, see how we're doing. Remember that when you're dealing with gas laws, it's really important to just kind of pull out the information, kind of label what it is a pressure, or volume, temperature. And a lot of times if you do that, and you're not really sure what gas law you should use, you could kind of see the gas law like looking at you. So for example, here we have a temperature that's 27 degrees Celsius. That goes with a volume that's 9.55 liters and a pressure that is 2.97 atmospheres. We have another pressure that is 8.25 atmospheres and a temperature of 125 degrees Celsius, and we're looking for a volume. So in this case, you could hopefully kind of see the combined gas law looking at you. We talked about this last time, just in order of how it's written in the problem. It's usually how we number these things, 1s and 2s. And again, that would give us P1 V1 over T1 is equal to P2 V2 over T2. In this particular case, we are looking for V2. Remember that the quick way to rearrange the equation is if you go across the equal sign, it ends up in the opposite location. So that means we'd have to move the T2 to the top and the P2 to the bottom, and that will rearrange that correctly. That's basically multiplying by T2 and dividing by P2 in this case. That will give us, when we rearrange it, P1, V1, and we're going to bring T2 to the top, divided by T1, and we're going to bring P2 to the bottom there, and that will equal our V2. Remember, whatever you're solving for does need to be on top, not on the bottom. If I solve for something that's on the bottom, that means I'm not really getting what I'm looking for. I'm getting 1 over what I'm looking for, so you'll have the inverse of what you're actually looking for. So whatever you're trying to solve for, it should be up on top by itself. And in this case, we do need to do a little conversion here. Atmospheres are good. Like normal, as I mentioned last time, it's almost a no-brainer in gas law problems. Pretty much just add that 273, get everybody into Kelvin. And if we do that, they're 125 and 273. Going to give us a 398 Kelvin there. And on the other side there, it looks like 300. I'll go this way with it. Now that we have everybody in the right units, we could put it in here. And again, we want to be careful to put everybody in the right spot. So P1's up on top, 2.97 atmospheres. V1, 9.55 liters. And our T2 is up on top, which is 398 Kelvin. That's going to be divided by our T1, which is 300 Kelvin. And on the bottom there, P2 of 8.25 atmospheres, and that's all going to equal our V2. Our atmospheres on top and bottom will cancel. Our Kelvin on top and bottom will cancel. That tells us that we're going to be left with liters as the units that we have here. So we're just going to multiply what we got on the top there, 2.97 times 9.55 times 398. Remember to hit equals at this point. Divide by the first number on the bottom, which is 300, hit equals. Divide by the second number on the bottom, which is 8.25, hit equals. And you're going to get yourself a 4.56 liters in this case. Any question on that calculation there? So again, if rearranging the equation is problematic for you, take some time to make sure you know how to, again, properly rearrange it. But really, if you want to keep it simple, just opposite location if you move it to the other side. Yeah, so it just ends up in the opposite location. Any questions on that there? All right, there's all our answers. All right, the next thing we're going to talk about is Dalton's law of partial pressures. And sounds like a very complicated thing. But again, we just want to kind of keep it simple here, which is the idea is if we had a container, for example, and within that container, the only gas molecule that we had flying around was gas molecule A. That would mean in this particular case, the total pressure of that container would be all result basically of just gas molecule A, basically, that's flying around, as that's the only one in the box causing collisions, right? Now, if we pop into a box here, or a container that can hold gases, and we put gas molecule A in there, we drop in there B, we drop in there C, we now have all these gas molecules, different gas molecules flying around in that container. And the total pressure in this case will actually equal the partial pressure of A, the partial pressure of B, plus the partial pressure of C. These are what are referred to as partial pressures because they are each contributing to the overall pressure of that mixture of gases. So the idea of partial pressures is pretty much this. If you have a mixture of gases, which is very common, and they're in the same container, the total pressure of that container will be a result of all the individual gases, basically individual pressures, and that is what is referred to as partial pressures. So how do we get the partial pressure? I would say probably the most common way that you could get the partial pressure of each gas is to use our friend the ideal gas law and solve for P. And you would solve for P, which would be nRT divided by V, and you could do it for each gas that's in that mixture. One of the nice things about this sort of mixture of gases is because they are all in the same container, you will have the same volume for everybody that's in there. And because probably that container is in the same room, obviously, it will have the same temperature for everybody. That means when you look at the ideal gas law that you're going to use, V will be the same for everybody, T will be the same for everybody, R is a constant, which means it will be the same for everybody. So really the only difference that you really will have to calculate for each of the gases that are present is N, which is the moles of gas. So the N will typically be different. And once you calculate the moles of the gases, you then can put them again individually into the ideal gas law. You would get 3 different pressures in my example here, one for A, B, and C. Again, those would be the partial pressures of A, B, and C. And to get the total pressure, you simply just add them together, basically, and that will give you the total pressure of that mixture. Any questions on that there? Now, when we look at these partial pressures, they should add up. And one of the reasons why we can sort of do 3 different calculations for these gases, even though they're in the same container, is because we are assuming ideal conditions. And one of the things that makes something an ideal gas is, as we might have touched upon a little bit last time, the idea that in an ideal situation of temperatures and pressures, you could have multiple gases in the same container and they pretty much will not interact with each other. So in an ideal situation, it's almost like they're in there by themselves. And that's how come we could treat these type of calculations like this, that they're in there by themselves, even though they're with other things, because there is no interaction. So having A, B, and C gas molecules flying around in the same container, they're not going to, in an ideal situation, interact with one another. So we could do 3 separate calculations like they were in there by themselves and then put it together to figure out the total pressure. So that is one of the main reasons why we're able to do calculations like this, is because we're under ideal situations, so we don't have to worry about any type of interactions between the different gas molecules. Any questions on that there? So here's pretty much what I just wrote there. Again, we're just going to basically do the ideal gas law for each gas separately and then add up each of the partial pressures when we're all done. Obviously, here we're going to use the ideal gas law, which means, again, we need to be careful about units. So as we talked about a second ago, obviously moles should be moles, temperature needs to be Kelvin, and volume needs to be liters. So everybody needs to be, again, in that right unit. And R obviously is still our gas constant, which you always have available to you. All right, so why don't you try one here? We got 5 grams of helium. It's added to 5 grams of neon. We put it in a 2.5 liter container at 27 degrees Celsius. We're looking for the partial pressures of each gas and also the total pressure. I'm going to give you some numbers that might be helpful here. Helium is 4.003 and neon is 2018. We're looking for 3 things. We're looking for the partial pressure of helium, partial pressure of neon, and we're looking for the total pressure of both of them together. Let's see what you come up with here. Again, basically an ideal gas law for each. Yes. Grams of helium. And we also have 5 grams of neon. We're going to put it into a container that is 2.5 liters. We have a temperature that is 27 degrees Celsius. And we're looking for partial pressures, which basically means we're looking for P. Obviously, here we have one of all information, so that should direct you really to PV equals nRT. Remember that although never given to you in problems, you always have R, which is a constant value. So here we're going to send volume to the other side really and solve for the pressure here of each of these gases individually. We do have the temperature, we do have R, we do have V. The only thing that we do not have in addition to the pressure that we're looking for is moles. But we do have the grams of each of these guys, and we can convert the grams into moles by using the molar mass from the periodic table. Hence these guys, yeah. So we could use those, convert them into moles, and then we'll have what we need, almost. So I'm going to do that first. So I'm going to look for my moles of helium. I'm going to take the grams of helium, which is 5. I'm going to use the molar mass from the periodic table as a conversion factor to convert from grams to moles of helium. And if I do, it's going to give me a 1.25 moles, I'll call it, of helium. I'm going to do the identical calculation here for neon, except obviously here I will use neon's molar mass, which again from the periodic table is 2018 grams per mole of neon. Going to get us 0.248 moles of neon. Any question on that calculation there? That I would say is also very, very common in gas law problems. You're given things in grams, you need to convert them to moles using the molar mass. Now that I have that, I have everything I need for the ideal gas law, except like normal, I gotta add my 273 here to my temperature to get it into Kelvin, and that looks like a 300 Kelvin. Our volumes in liters, so that's good to go. Remember as well, a very common conversion is milliliters to liters or liters to milliliters as well, that you need to kind of do. So I'm going to start with the helium here. The partial pressure of helium will equal nRT divided by V. Putting in the moles of helium, 1.25 moles. Putting in my gas constant, 0.08206 liters atmosphere Kelvin mole, and my temperature of 300 Kelvin, all divided by my volume of 2.5 liters. The moles will cancel, the liters will cancel, not the, sorry, the liters will cancel, the Kelvin will cancel, cross out the right one there. And we will be left with atmospheres, which is good since we're looking for a pressure in this. Again, make sure you hit equals after the top line there. We'll call it 12.3 is known as the partial pressure of helium in this particular case. Question on that there. We're pretty much just going to repeat that. Other gases in the container, and because they're in the same container, again, they have the same volume, the same temperature. It's pretty much the identical calculation, except I just need to use the moles for my neon instead of obviously helium. So if we do our pressure of neon, it will still be nRT divided by V. The real difference here is we're going to use the moles of neon, obviously, instead of helium. Everything else is going to be identical, exact same values, because frankly, they're in the same container. They're under the same conditions. The only difference is how many moles we have. Same cancellation here. If I wrote moles, moles cancel, Kelvin cancels, liters cancel, leaving us atmospheres here. And we will end up with 0.248 times 0.08206 times 300 divided by 2.5. It's going to be a 2. The last thing that I'm looking for is the total pressure. What should I do with those two numbers? Yeah, we're just going to simply add them, right? So partial pressure of helium plus the partial pressure of neon would get us a 12.3 atmospheres plus a 2.44 atmospheres. And you throw your calculator in the sink, you get it out of the sink. 12.3 plus 2.44, 14.7 atmospheres would be our total pressure. Any questions on a calculation? It's basically just the ideal gas law. Again, volume, temperature, the same for everybody in the mixture. Really, the only difference is going to be the moles, and then you add them together at the end. Which one's contributing more pressure? Helium or neon? Yeah. The reason for that is, let me know. It has to actually do with these numbers. Helium is much, much lighter. Yeah. So since it's lighter, it's going to actually be flying around at a very high velocity, much faster than neon. And because it's flying around a lot faster, it can cause more collisions and more pressure because it's a lighter gas molecule. It's going to cause a lot more collisions. Any questions on that there? Cup. Now, another very common sort of partial pressure situation is maybe this one that looks familiar to you. Maybe. Terrible lab. Was something like this when we collect gas in the laboratory. A lot of times, based on the way we collect it, we cause sort of a situation to occur. So this is a little potassium chloride action here, which I think you might have done. And if you heat the heck out of that thing, it will decompose into a little potassium chloride and a little oxygen gas in this case, right? And in this case here, we do a little balancing, I suppose, would be good. 2, 2, 3, maybe. And in this case, we're going to produce oxygen gas. So as you heat this, and hopefully you put a bunch of that in there, otherwise you're probably there all day. If you didn't put a lot of that catalyst in there. The oxygen gas will come through this tube into this container where you typically have water in it. And as the gas goes into the container, the water goes out of the container, sort of displaces it. And you end up with this empty spot usually in your container. It's really not empty. It actually has the oxygen gas that you generated in this particular example. But as a consequence of how this water or this gas was collected, water is involved. And when you do a little reaction with water, it doesn't take a lot for it to heat up. And you will also collect some water vapor. So what you end up with in this case is actually a mixture of two gases in your experiment. And frankly, you're not interested at all in the water. You're really just interested in the oxygen part. So you get the total pressure in this case would equal the partial pressure of the gas you're interested in times the plus the partial pressure of water. And that's what is sometimes referred to as the vapor pressure of water. And that usually is a value you can look up on a table. That's usually a value you can find on a table. And we can use this, and in the laboratory, that's your barometer reading for today. That is usually what that value is. And you can use this equation and actually rearrange it, and the partial pressure would equal the total pressure minus the vapor pressure of water. It's kind of like a correction value that you typically do in experiments like this to subtract off the contribution of water because you're frankly not interested in it. You're really interested in my example here of the oxygen gas that you collected. You're not really interested in what water's doing and stuff like that. So the nice thing about this type of partial pressure one is it's just a subtraction type of problem. So you take the total pressure, which is again usually the barometer reading, minus the vapor pressure of water at the particular temperature that you may have to look up in a table. And that will get you the pressure of the gas. Sometimes in labs and stuff, they refer to this as the pressure of the dry gas. And that is because you subtracted off water's contribution basically to the pressure in this case. So anytime you collect a gas and water is involved, you usually have to do this type of correction sort of calculation, which is really, again, a sort of partial pressure situation that's happening. All right. So let's take a look at one here. A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of the gas in atmospheres? So this is basically the exact same situation we were just talking about. The key words that you know that you typically have to do this in a problem is it will say something like this. Hey, it's saturated with water vapor. Or they'll say you collected it over water. They'll mention something to do with water, and that should automatically to you kind of pop this equation into play. And in this particular case, they were nice enough to give us the vapor pressure of water at 30 degrees. And in this case, it is that number there, 31.824 torr. The total pressure, or the barometer there, is 753 torr. So we have this guy, we have this guy. So once again here, we can rearrange for the oxygen gas by subtracting this to the other side. And that will give us that the total pressure is minus the vapor pressure of water. And if we put our numbers in, we will have 753, which is our total pressure, minus our table value. And again, if it was not given to you in the problem, which commonly is probably not going to be, you need to look it up in a table that should be in that gas chapter. And it's usually based on temperature is sort of what you look it up as. And we'll take 753 minus 31.824. Going to yield us something like 721 torr. We are looking for it in atmospheres, and that is where that 760 number comes into play. 760 torr is 1 atmosphere, so those guys will cancel. And that will get you, we'll call it 0.949 atmospheres as our basically pressure of the oxygen gas in this case. And that's the dry oxygen gas getting rid of our sort of water contribution. You could also do this type of partial pressure problem if you know basically the total pressure of the mixture and you know one of the other partial pressures, or if you know obviously both partial pressures, you could add them together. So you kind of use the adding and subtraction fairly easy if you know kind of 2 of the 3 things, or 2 of the 3 things, depending on how many gases you have going on. Any questions on that there? So this is the kinetic molecular theory of gases, and these are some important parts that you should know. Gases consist of tiny particles or atoms or molecules. These particles are small compared to the distances between them. So the volume of the individual gas molecule is not important. So as I mentioned, I think the other day, that's why when you read a lot of problems, they talk more about like the volume of the container the gas is in, rather than the volume of the gas molecules themselves. That is one of the things that makes something an ideal gas. We ignore the actual volume of the gas molecules themselves. Is more important the volume of the container they're in, that they're flying around in, rather than the actual individual gas molecules. Because their volume compared to the volume of the container they're flying in is much, much smaller and almost negligible in that calculation. The particles are in constant motion and colliding with the walls of the container. These collisions, again, is what causes the pressure we exert, or we think of with gases. The other gas is this one right here. And that is, as I mentioned before, that we assume that there's no attractive forces or repulsion type forces in an ideal situation. So again, that is why when we do our partial pressure calculation like we just did, we can basically do the ideal gas law for every gas individually, even though they're all in the same container. They're not going to, in an ideal situation, have any interactions with each other. And we can almost assume like they're in there by themselves, which allows us to do that type of calculation. If you're dealing with a real gas, which we do not deal with in here, real gases, you do have to actually take both of those things into account. The size of the gas molecule itself and actually its interaction with other gas molecules. It creates the ideal gas law that looks really scary looking, and it's known as the van der Waals equation. But that only occurs at really high pressures and really low temperatures as well. But we don't deal with that. So everything in here will be an ideal situation. The average kinetic energy of the gas molecules is related to the temperature. Temperature increases, we expect the gas molecules to fly around faster. If it decreases, we expect them to kind of slow down. Any questions on that there? Just to finish up on some of the parts and relationships that we talked about. Again, temperature is a measure of the motion of gases. At higher temperatures, we have, again, those gas molecules moving faster, hitting the walls of the container, again, could be increasing the pressure. Lower temperatures going to be moving slower the gas molecules. We would expect less collisions. Pressure and temperature, the pressure in a rigid container, so that's going to be a container like in a Gay-Lussac situation where the volume will not adjust. And in that situation, the pressure will start to increase As you increase the temperature, as we talked about, again, just because they're going to be flying around faster, volume's not going to move, a lot more collisions, a lot more pressure. Opposite is true, obviously, if you lower the temperature in that situation. Volume and temperature, remember again, in Charles' situation, it is the volume that adjusts to allow the pressure to remain constant, and it will adjust the same way as the temperature. Temperature increases, the volume increases, gives everybody more room to fly around in, and temperature decreases, the volume will squish them down and put them closer together. Any questions on any of that there? That is chapter 8, the